her in London because she teaches and does music research at the Queen Mary University. Ladies and gentlemen, please welcome Professor Elaine Chu.
So today I'm going to speak about motion and gravitation in the musical spheres. And this is an attempt to connect my own experience of music with conceptualizations of how to shape music in relation to what we know as movement and motion in the three-dimensional space that we live in. And this is the basic outline of what I'm going to talk about. And we'll begin with some ideas of gravitation and motion, and then I'll talk about applications in tonality and in timing before drawing some final connections. So first of all, tonality. And tonality is a key concept in music. And I'm going to demonstrate that all of you understand tonality by asking one of my fellow speakers to play the first part of the theme of the second movement of the Schoenfeld Trio, which we're going to play later this evening. And Iran, if you could just play the notes that are up there. But that's good.
Oh.
The next four.
Okay.
Thank you. So the idea is to demonstrate that you can understand when a melody is finished and it's not finished. So how many of you are satisfied if Iran just stopped right there? Yes? 1.5. Who would like him to finish it? Most of you, but you're going to have to wait. We will do that in a bit. The reason you know that it's not finished is because you've already established in your mind what the tonality of this melody is. And I'm going to demonstrate how tonality can be thought of in terms of gravitational pull. You've heard the dum, bum, bum, bum. You wanted to do something more. And I guess as the composer, Paul is here, he can decide what else he wants to do after that. And that was one particular, this piece has one particular completion of that melody. So gravitational pull, we're all familiar with that because we live in the solar system where there are these heavenly bodies and they exert gravitational pull on one another. And we live on Earth and we experience gravitational pull. We feel it when we walk around. It's part of our everyday life, and we negotiate it. We learn how to negotiate it from the time we're a baby, learning how to walk, to, trying not to fall when we're older. And lots of scientists have tried to model this experience of gravitational pull. It's been around for, I guess, for hundreds, maybe even thousands of years, including, for example, Copernicus' heliocentric model of the solar system. These are all done with mathematical equations. Newton's law of universal gravitation, Newton's law of motion. I got this from the NASA website. The law number 1 says every object persists in a state of rest or uniform motion unless it's compelled to change its state. The second law says the force is equal to change in momentum per change in time. So force for an object of constant mass, F, the force is equal to mass times acceleration. And the third law says that for every action, there's an equal and opposite reaction. So as musicians, we often employ these analogies in our shaping and manipulation of music and being expressive in music playing. So before I get into that, I'm going to show how tonality itself can be modeled with concepts that are similar to this concept of the center of gravity and gravitational pull. But before I can get to that model, I need to give you some context and background to the model. The model was inspired by some work that I had done as an undergraduate with George Danzig. George Danzig is formerly better known, not for the gravitational center of gravity algorithm work, but more for his work on the simplex method, which is used to solve linear optimization problems. And this is an example of a linear optimization problem with constraints, and the solution is supposed to be found in that red shape in the middle. And what you do is you start with some initial, let's say that's the optimal solution. You start with some initial solution, and you walk along an edge to another corner point solution, and along another edge to another corner point solution until you reach the optimal solution. And once you get there, you're done, and you've solved the problem. The problem is that for linear optimization problems with more constraints or in higher dimensional space, this could be a very long process, and it's, although in practice quite efficient, theoretically it's not very efficient. In the late 1980s, Kamakar came up with another method of solving linear optimization problems called the interior point method, where he just did away with staying in the feasible edges and and traveling on the outside of this shape, and just went straight through the middle to zip straight, zooming in towards the optimal solution. And this was in the late 80s, but unknown to many people at that time. Back in the 1950s, von Neumann had already proposed an interior point method that he had communicated to George Danzig, and George Danzig later on was to continue some of this work. So the idea is that any linear optimization problem could be reformulated to be a problem where you have this ball in some high-dimensional space, and there are these points on the surface of the ball, and you're trying to find some subset of the points on the ball that cover the center of this ball. And for example, this shape, if you took all the points, you would cover the center, and you could then find some weighted combination of the points on the outside to then solve to get to the center. These 3 points outlined by the triangle also would cover the center, so would these 3 points, and so would those other 3 points. But this is a particular easy example, which allows me to show you how the interior point solution, how the algorithm actually works. So we have this ball and points on the surface. We start with a single point on the surface. We shoot a line through the middle. We have a perpendicular plane to it, and we look for a point on the other side of the plane that makes the smallest angle with this line. So you get this line over here, and then you drop a perpendicular to the line from the previous point to the point that you use to triangulate to get closer to the center. And then you now have a point that's closer to the center, and now with that as your current solution, you then shoot another line through the middle and have a cutting plane and find the other point on the other side that makes the smallest angle with that line. and again triangulate and drop a perpendicular to get another point even closer. And you iterate again, and you draw a line through there, perpendicular and smallest angle, and triangulate and drop another point. So you can see that you progressively get closer and closer to the center and then come to a solution for the problem. So this was in effect an inspiration for a key finding algorithm that I had come up with in my thesis that was called the center of effect generator, which is based on kind of the center of gravity idea. So in tonal music, a representation of tonal music that's widely used is the harmonic network, or the tone nets. And the tone nets is aligned so that all the pitches along the x-axis are aligned, are basically perfect fifths of one another. And all the pitches on the vertical axis are major thirds. And if you look and stare at this for just a minute or two, maybe you'll notice that the pitch names actually repeat. So the D is repeated again over there. And if you wrap it up, in the days of the transparency, you could take this grid and then wrap it up and then put the two Ds together and staple it together. And you would see this shape emerge, which is then a spiral, a helix. And you get this helix. Once you're in three-dimensional space, you can start playing with the interior of the space. So we now start playing with the interior. So we still have the triangles that represent the triads. And all triangles like this represent triads. We can represent the triads as a point in the middle of the triangle. And these triangles, these points representing each triangle themselves form another helix in the interior. And three adjacent triangles gives you all the pitches in the key. They are basically and so you can then define keys as being three adjacent triangles and represent each key with a point that is in the middle of each triangle that outlines all its basic triads. And so then we have another interior helix representing all the keys. And this way we can generate also in a similar fashion the minor key representations and minor chord representations. And so in this interior space, a key would be this convex shape, and we could have a center point in this convex shape that represents the key. And when you encounter a melody like this, so you would go, you start with the first note, dum, you map it to the outer helix, and when you get the second note, dum, dum, the second note is to the left, and it starts pulling it, the center, towards the middle of the 2 points that are the pitches. Dum, dum, and then again, da. The second time you get that pitch again, it starts pulling it further that way. Dum, da, 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 da. Okay, and so on. So as you get more and more notes in the melody, you get closer and closer to the key representation. And once you look for the closest neighbor key, you'll find that you have an automatic key recognition algorithm. This algorithm was implemented in MuseArt, and I'll show you by Alex Francois using his software architecture. And this is a video showing how it works. So this is Bach's Prelude in C major, and I'm going to play just the first chord. Okay, so I've played 3 pitches, C, E, and G, and you see the silver blobs. C, there's a hidden silver blob here, E, a silver blob, and G, and these indicate the pitches that are sounded, the pitch classes. And this means that the triad
of C is the closest triad in this case, and that lights up as a triangle. And the closest key, which is on the helix here, that's the major key helix. The C major key lights up, and it's very close to the triad, so it's rather large. The size of this blob indicating the key, which is also shown out here as the dodecahedron, is proportional to how close we are to that key. We're in the chord of C, in the key of C. Now the chord is D, but we're still in the key of C. G chord in the key of C. C chord in the key of C. A minor.
So you basically get the idea of how this works. And here's an example of it outlining the ground bass in Pachelbel's canon, which is basically the same chord sequence repeated over and over and over and over and over and over again. So you can see the lines have been traced over many, many times. I started in the middle of the piece, and it's going to continue doing this until the very end of the piece. We haven't tried this with Ravel's Bolero, but that would be another good example. Okay. So what can we do with the space now that we know that it can be used to recognize key and chords? What else can it do for us? So one way that this representation can be used is to model the idea of tension and release. And we have here an example. I'm not going to play that particular video from the Schoenfield Trio. And now, actually, Iran can finish the entire melody.
So you start from the top again?
Yes, please. Thank you. So that is the theme from the middle movement. And if we put that theme into Musart, so you will hear there was a moment at the beginning where it does something weird. That's slightly out of the key. That is out of the key. Okay, so when there's something unexpected, it shows up as something that's distant, and so creates a little bit of tension because it's unexpected and not something that you would hear normally in that key when it's in its plain vanilla form. And when something is unexpected, then the player has the opportunity to do something with it or not. If it's very expected, the player can choose to do something to obscure it. So this is where expressiveness comes in. And now we move on to motion and time. At one point in time, following some of Iran's games, we also tried our hand at creating a driving game, this time manipulating expression, where when you accelerate the pedal, it was a driving game, so taking if you think of playing music being like driving, and especially if you're a pianist, it feels a lot like driving. You're sitting behind a huge machine, you're pressing pedals, and you're playing, and you're just thinking about going faster or slower. And so if you have this as a car, if you think of this as a car and you're accelerating and decelerating, you can start shaping the music over time. And we did have this interface, and as Iran mentioned earlier, I got bored with it after a little while because it just didn't allow me to do the kinds of things I could on this machine, not quite as finely as I was used to. It was fine for making huge gestures, big shapes, large phrases, but the kinds of details and the enjoyment I get from being expressive at playing was just not available. So now I'd like to talk about when we take the idea of having something unexpected, or maybe something very expected, we can start playing around with time. And this is where the idea of tipping points comes in. A tipping point is a point in time that is timeless, is a suspension of time, it's a stillness, a stasis, beyond which a small perturbation, like this, will tip the balance and set in motion the inevitable return of the pulse. So those moments, an example of such a moment can be found in this performance by Martha Argerich in a cadenza. Okay, so a cadenza is basically a long elaboration of the cadence, a 5/1 cadence. That's a very plain vanilla 5/1 cadence, and she's going to have many of those. She's going to dwell on the 5, 5, 5, 5, 5. You know it's going to go to the 1, but it keeps being delayed. And finally, when the 1 is about to come, she sort of holds it back before releasing and going into it. That's the 5. And then back into that. Yeah. Oh, you have to hear that. Okay. So the reason that moment feels so good is because there's been this sort of heightening of expectation as it develops your expectation for what is about to come. And if you look at what tonally the music is doing, you know, it's 5, 5, 5, 5, 5. Oh, wait. The 5 sort of hints at the D minor that is going to go back into. And the 5 here is the A major, and you have these long passages of alternations between A major and D minor, A major, D minor, A major, D minor, until finally A major, we're about to finally fall back into D minor, and it finally tips over and returns to the D minor. And, I'm not going to do this. And you can see in the timing of 3 different pianists here, before the final tip comes in, that goes back and leads you back into the return of the theme, you will have this long elongation of time. I mean, it's this is the length in seconds of each bar. So that was like 4 seconds long as opposed to typically what might be around 1 second long. And so you can see that performers take extreme, extravagant gestures to sort of announce and augur the return. And this is where we get another example from cafe music. I don't know if Paul is willing to play or ready to play, but I'll play an example from the audio and maybe do something different, or how would you prefer to do it?
Okay.
Okay, so this is Paul playing. This is an excerpt from the second movement of cafe music. And I'm going to show you what that actually looks like if you try to tap along to it. This is Sonic Visualizer. It's been developed at Queen Mary. And once you've done that, you can then look at a plot of the amount of time taken for each eighth note. And there is the tipping point in this particular recording. And I've asked Paul if he's willing to do something different. And so we can hear what that might sound like if he decided to do something different.
Probably mention I made that when I used to practice, but I don't practice anymore.
Okay, Paul would like to say he doesn't practice anymore, so just to let you know, I mean, that was recorded when he used to practice. So as you can see, there are many ways to have these push and pull feelings, and these feelings of gravitational pull in the playing of music, in the composing of music, and to create them at will. And so this is basically the idea that I'd like to leave behind, that there can be gravitational pull, feelings of gravitational pull from the feeling of the tonic, wanting to pull things back to it, and also gravitational pull of the pulse, wanting things to fall back into a more regular periodic pulse. And so what is next? Well, perhaps we can start looking at centripetal and centrifugal forces and how we generate those kinds of feelings in music and how we can model it. Okay. So, thank you.
Thank you very much. Thank you very much. That was absolutely super and so revealing. We've come now to the question and answer part of our session this morning, and I thought I would kick off with a question for all of you, actually. You know, people often say to